As I said already, climate change affects all of us, and especially in the last 150,000 years there have been numerous abrupt changes, especially in the sea levels in Greenland. Let me say a few words about our speaker today, Dorthe Dahl-Jensen. She is from the University of Copenhagen and the University of Manitoba in Canada. She did her PhD in 1988 in Copenhagen. After that, she had postdoc in the University of Melbourne. And after that, she started as an assistant professor at the University of Hobart, which is south in Tasmania. After that, in 97, sorry, she started as an assistant professor, associate professor at the University of Copenhagen, and where she is now a full professor since 2002. After that, or just recently, she also has an affiliation with the University of Manitoba since 2019, where she holds the Canada Excellence Research Chair. She has numerous distinctions. Let me just mention a few: the EU Descartes Prize 2008, Vega Medal, Amalienborg Prize, Munch Prize, Louis Agassiz Prize 2014, the Rossby Prize 2020, and the Balzan Prize in 2022. She is also a member of the Royal Danish Academy of Sciences and Letters since 2015. And with that, let me invite Dorthe to the stage. Greenland ice cores tell tales on past sea level contributions. With that, Dorthe, please take it away.
Thank you very much. So I hope the sound system is good. I've tried to put some slides together to tell you about what we learned from Greenland ice cores about the past sea level rise. So I'll just go ahead and start. So there's so many things I can tell you about that I always have to make a selection of things I want to tell you about. But today I want to tell you a little about what's happening with the climate right now. Then I want to talk a lot about the ice cores from Greenland, where I'll talk about the water isotopes and volcanic eruptions and greenhouse gases. And finally, I'll tell you about our present deep ice core drilling project that we call eScript. So that's kind of the agenda, and I hope I can make it all in this 45 minutes I have. So first of all, I want to bring a great hello from my research group in Copenhagen, because I think, as you all know, this kind of research is not something that's done by me alone. It's done by a big research group, so I cannot take the honor for all of the things I'm going to tell you about. It's a group effort to do it. So I'd like to acknowledge the big Danish group and also international groups, and actually also a group here from Stockholm's University. So our focus for many years has been to contribute to an improved understanding on past warm climate periods by studying ice cores and using models to explain what we see and try to predict it into the future. So it's interesting that the climate has had warm periods before, and of course, by studying those, we learn a lot about how climate can change. Now we are a really old research group, probably one of the oldest ice core groups at least. It was founded by our professor Willy Dansgaard, by the way, it was 100 years since he was born last year. He was the one that discovered that he could take a mass spectrometer and he could take water and measure the H2O and use that to reproduce past temperatures. And this was kind of the foundation of ice core research. And since then, our group has grown. So now we've drilled a lot of ice cores in Greenland and also a few in Antarctica. And we are a group of 50 to 70 people at the University of Copenhagen. Willy Dansgaard has written a book, Frozen Annals, that's quite fun to read, with all the good old stories from the first time of ice core research. And you can find them on our homepage. You can see the link there, iceandclimate.dk. There's a lot of information there about what we're doing, by the way, if you're more interested. So our group has really founded a lot of the ice core research. We have developed the ice core drills that we use for drilling the ice cores, and I'll show you more about the ice cores later. But we've also discovered or developed a lot of the methods we use to measure ice cores. So for example, automatic mass spectrometer, so we can measure many stable water isotope samples every day. We've developed a lot of models to use. We have developed a method to measure electric conductivity, ECM, where we simply drag 2 electrodes along an ice core, and in this way we measure the current that can go through the ice, which, for example, shows all the big volcanic eruptions in the ice. We've also developed methods where we can take sticks of ice and melt them and measure countless amount of impurities and insoluble dust. And one thing that's very smart there is that you can cut the block and you can make your melt system so you only melt the center of your block, so you don't have to clean the ice before you measure it. Because the ice we have on the Greenland ice sheet is very, very clean. A lot cleaner than distilled water. We've developed the drills and also loggers. So I think one of the things that really classify the group is that we are so multidisciplinary, that we kind of do everything. And it is the group that does it. We don't have a big logistic organization that does it for us. So all the professors help to move the boxes, all the students help to drill the ice cores. So it is a group effort to do it together with all the groups, the people from other nations that are involved in the project. And I think that's also a strength, that no one is too fine to do anything. We just help each other. So you can see here some of the pictures from the camp. One of the smaller surface drills. We fly with the National Science Foundation and the US Air Force. They are the only ones that have a fleet of Hercules with skis on that we use to get to our camp, which is about 1,000 kilometers from the nearest airport along the coast. You can see here 4 rockets on the side. If it's hard to get off the snow, sometimes they burn these rockets on each side to get more speed. And it's always really, really interesting when you're sitting in the plane, if you are in the air when they burn out or you're still on the snow. We also build our own infrastructure on the ice, the dome, for example, because when we get to the places where we drill the ice cores, it's just a pristine white desert. So everything we have is something we have brought to the camp. So this was just an introduction of our research group, and with that I'll talk a little about the climate. So first of all, I'll show you a movie here of how the global temperature has changed since we started having enough weather stations to be able to have a measure of what the temperature is around. So you can see, first of all, that it's not just equally colored everywhere. Climate change is very varying. Sometimes it gets warmer, sometimes it gets colder. Red is warm, blue is cold. But as we approach 2000 and go beyond 2000, you can see that it consistently gets quite red up in the Arctic area. It also gets much warmer in the Arctic area than it does around Antarctica in the south. You can see Western Antarctica here warms, but if you follow the coast along Antarctica, you can see there are also spots where it's actually cooling. So I think that's worth noting, that when we talk about the big climate changes and what's happening, it's really the north that's reacting now, because as it gets warmer, of course, the ice melts. So we can compare this with sea level rise. So here's a map where they, by satellite, have measured sea level as an average in this period here, 93 to 2012. And it's also quite interesting to see this map, because sea level rise is not something, again, it's not equally distributed around the Earth. It's not like putting water in your bathtub and then you're getting the same level everywhere. And of course this relates to different currents, different salt contents, and different depths of the ocean, so it warms more in the areas where it's shallow. And this is very pronounced over here in the Pacific Ocean, where you can see the purple colors represent sea level rise of more than 9 millimeters per year, which is basically 2 to 3 times more than the average on our Earth. You can also see here along the west coast of America that you actually have a lowering of the sea level here, while you have an increase on this side. So it's really different from place to place how the sea level has been. But if we try to zoom in on Denmark and look at the predictions for what sea level rise will be in year 2100, you can see here that what the wise people say is the sea level rise will be about 70 centimeters plus minus 60 centimeter. And I think this is the very depressing thing. Some people call it the most dangerous uncertainty because, there's quite a difference in the actions a country has to take if it's 10 centimeters or it's 130 centimeters, you have to, protect your land against. And Denmark is a rather flat land, so there are areas that we need to protect if we get these high sea level rises. So that's kind of our quest with our ice cores, and especially the program we're doing now at eScript, to see if we can constrain this uncertainty and bring the uncertainty down, because I think that's super important. So another way to look at that is to look at all the figures from the big climate report from FN, the IPCC reports. I assume you have heard about those. Most people have in some way. They, every 4th or 5th year, they come with a report where they report the state of our climate system in the first report, the physical report. And this is kind of a timeline here. This is 20 years ago, and then we go towards now. And it's the prediction of the sea level rise from the two big ice sheets, Antarctica and Greenland alone. So it doesn't include the thermal warming of the ocean or other contributions. And you can see, if you go back in time, they expected a small contribution in year 2100 with a very little error bar on it. But as time goes, it wobbles very much up and down, and it grows to higher values here. But one thing I think is very notable is that the error bars, the uncertainty, increases with time. So here we are, we work, we dig, we drill ice cores, we stand on the ice sheet every year, and as a result, we seem to know less and less. And this actually illustrates, we know very little about the behavior of the ice sheets, especially the ice streams around Greenland, and we are realizing this as time goes, and we get to know Greenland better. So it's really an area we need to focus on, especially the ice streams, if we are to bring this uncertainty on the prediction of sea level rise down. This is my kind of quest in life, I think. So we can look at where is the ice on Earth. So if we take Greenland, we can see it has an area and it has a volume, and if you melt it all, the volume is equivalent to 7.4 meters of sea level rise. If we take Antarctica, it's certainly the big brother, it's 10 times bigger, and if you melt it, it's 73 meters of sea level rise. Now, Greenland is more exposed right now because the Arctic is warming. So for now, Greenland is our greatest concern, but that doesn't mean that Antarctica won't start reacting as we continue to warm. If we look at all our small loved glaciers everywhere, Sweden, Norway, Iceland, the Alps, everywhere now in there is, and you melt them all, it's only 0.6 meters of sea level rise. So when we talk about big sea level rise, you really have to focus in on the big ice sheets. That's the only source we have. Now I just put sea ice on the figure here as well. This is the sea ice. You see the annual cycle of sea ice running on the frames up here. And you can see that they cover a very big area, but of course, because they are already floating on the water, they don't contribute to sea level rise. But of course, they contribute a lot to the reflection of sunlight from the sun. So it's really important if we have sea ice or not. It's just not important for the sea level rise. So now, I'm going to take you to Greenland. And I'm going to introduce to you a very, very smart way of observing how the volume of the Greenland ice sheet changes. There's a system called GRACE. It's 2 satellites that orbit the Earth, and they simply measure different positions of the 2 satellites. So what they're really measuring is the gravitational attraction from Earth. And of course, they can measure the gravitational attraction of the Greenland ice sheet, and as the Greenland ice sheet loses mass, the gravitational attraction will change. This is what it was shown on this graph here, since 2002 to 2016. And you can see here, this is the mass loss in gigaton. And you can see that every winter, the Greenland ice sheet gains mass, and every summer, it loses mass. Some years are exceptional. For example, I'll point to 2012, where there was a big mass loss on the Greenland ice sheet. On this graph here, the arrows show the way, the direction the ice is flowing, and the red and blue shows how the elevation has changed during this period on the Greenland ice sheet. So you can see here, this is the place where we have Ilulissat and the big Jakobshavn ice stream here, and you can see that the area inland from the ice stream has been lowered with 4 meters. You can see along the coast, in general, you see the lowering, But if you look very carefully, you can see that in the center, it's actually light blue. So where we drill the ice cores, the surface is actually going slightly up. And of course, as it warms, the clouds can also contain more humidity, so the snowfall increases in the center part, but of course it melts a lot along the margins. So if we try to sum this up and look at the slope of this curve here, over this period here, the general mass loss is 280 gigaton per year, and this is equivalent to 0.8 millimeter of global mean sea level rise per year. The other curves showed that the value was 3.5 millimeter per year on average, so Greenland is contributing with about a fourth of the total sea level rise at the moment. But it's also worth noting that the Greenland ice sheet is about 3,000 meters thick in the center, so it's an enormous volume of ice, and we're actually only melting 0.01% every year. So Greenland is not going to disappear in few years. It's going to be thousands of years before it disappears. You can also imagine the amount of energy that's needed to melt such a big lump of ice. It has to come from the sun before it can melt, right? So it is it's more resilient than some people kind of tell you, is my kind of experience. So now let's go and look a little at the ice cores. So we go to Greenland and we drill the ice cores. Here is one of our professors, Bo Winter, cleaning a surface of an ice core here. And when I start these stories, I always tell people that we are not fortune tellers. We're not looking into the future and trying to predict what's happening. We're looking back in time, and we observe how things have been back in time. So we're actually wise men. We're looking at things that have happened, so it's not kind of fiction. It's true things that have happened in the past. And of course, we try to project them to the future to tell, what we think is going to happen in the future. So Gunn is the fortune teller. Let's go down and look at what we're actually doing. We go to the center of the Greenland ice sheet, and we make subsurface trenches where we do our work. Here is a trench where we drill the ice cores. Out here is the ice core in a horizontal position, and they're always made so they can tip around the center point, and then we lower them down into the borehole. The drill is about 13 centimeter long, and it's hanging in a cable. So the way we lower it down is just, in reality it's very simple. We lower the tool down to the bottom of the borehole, then we screw the drill down into the ice until we have 3.5 meters in the hollow inner tube. And then we pull backwards with our drill, and this is the cutters that cut the ice core here. And when we are finished drilling, then we pull backwards, and these bronze things, they tip into the ice, and then they break the ice, and we pull the drill up to the surface with the 3.5 meter of ice cores inside. So it seems simple, right? Of course, there's a lot of tricks in it. Here you have some anti-torque section where you have some metal bands that go out towards the side of the hole, because if you try to rotate something that's hanging freely in a cable, it's not going to work. Secondly, you can see that the ice core is smaller than the cutters, and you wouldn't be able to pull the drill up and down if this wasn't the case. So you produce a lot of ice cuttings when you do this, and they are circled up between the two. There's two hollow shafts here, and they are pumped up and kept in the chamber over the ice core. So there's a lot of tricks to the trade. It's not so simple to do, but we can do it. That works. So when we drill the ice core, we measure a lot of things in the field before we take the ice cores home for further measurements. And I have a little movie here trying to illustrate this. Here's the ice core buffer with the ice cores, the 3.5 meters of ice cores. We take them into our science trench here, where we have a team of scientists working. And the first thing we do is we cut them in different slices for the different measurements that we are doing. And when we've done that, we measure some of the first properties on the slice. You can see here we are scanning the ice core. We're looking at the visible properties on the surface of the ice core. And we are also dragging 2 electrodes over the ice core, measuring the electric properties of the ice. The last thing we do is we have a post office where we simply, after demand, cut a lot of samples that we bring back to different science groups that have programs that they want to measure on the ice core. I like this Busy Bee movie because I think there's not two people from the same nation in the science trench, and I think it's wonderful to see how everyone is helping each other all the time. So it's a very dynamic game that's happening there. So that's the start of an ice core. We measure, we drill them, and we start measuring them. And then I'm going to show you some of the results we get from the ice core. So here's one of the major results. I'm sorry the X went away. But this is thousands of years before present. So 0 is the present. This is 20,000 years ago, 100,000 years ago, and 140,000 years ago. And on the second X, we have the delta 018, which is the proxy that our Willy Dadsgaard discovered as one of the first ice core measurements. And I have not put a lot of slides in explaining this, but in reality, H2O, water, is genius to measure on ice cores because it's everything. It's not a very rare thing. It's the whole bulk of the ice core. But H2O, the oxygen especially, can have 2 atomic weights. It can have the atomic weight 16, which is the most normal, and it can have the atomic weight 18, which is more uncommon. There's 2 out of every 10,000 that are 018 compared to 016. But because 018 is a little heavier than 016, then as the cloud moves from the place where the water evaporates up to a cloud, normally in the subtropics, then it snows and rains from the cloud, and every time it snows and rains, then there's more of 018 that goes out relative to 016 because it's heavier. So the cloud becomes more and more depleted of 018, and it's this depletion which is the delta value here of 018. So the more negative it is, the more depleted the cloud is of 018, and the colder the cloud has been, because the amount of vapor left in the cloud is proportional to the temperature of the cloud. So this is the cold periods, and this is the warm periods. And if we look at a record, in this case from the ice core site we call NAME, the red one here, we get this wonderful record reaching 128,000 years back in time. If we make a line that shows the temperature as it is now, we can see that there are 2 periods in general that has been warmer than the present. In our present interglacial, we call the Holocene, we have a period here, 5 to 8,000 years before now, where the climate was about 1 to 1.5 degrees warmer over Greenland. We call it the climatic optimum. And if we go beyond all the ice from the glacial period, back to 115,000 years ago, to 128,000 years ago, we have this big warm period that was our last interglacial, and we call it the Eemian. This, of course, is really, really interesting because you can see it's quite a lot warmer than our present temperature. So what happened at this time? How did the Greenland ice sheet survive? It's kind of one of the major questions that we can answer when we look at the ice. How warm was it? And especially from the NAME ice core, we have really studied this. So I'll try to walk you through these curves from one of the publications we have. The black curve is the measured delta 018 compared to the present values here. You can see the 018 values here and the present value here. Then we have corrected them to temperature, but we've also made some corrections because the ice near the bed was not originating on the surface exactly the same place as where we drilled the ice core. There's been some flow with time, so we have to correct that it actually fell somewhere else on the Greenland ice sheet. So we end up with a red curve here, which is our temperature reconstruction at the NAME site of the temperature back in time. And you can see it was actually 8 degrees warmer here at the onset, and then you can see it slowly declines, and here when we reach 118,000 years before present, it gets colder than the present temperatures we have right now. So in general, it was a warm period. We normally say it was an average 5 degrees warmer than the temperatures we had in the pre-industrial period. So what happened with the Greenland ice sheet during this period? Now we do something else, because when snow falls in the Greenland ice sheet, it's very fluffy, and there's air in the matrix. But slowly you get more snow on the surface and more snow on the surface, and the snow is compressed to ice, which happens in a depth of about 70 meters on the Greenland ice sheet. But some of the air becomes trapped in the ice matrix. So we end up with small trapped air bubbles in our ice cores that are actually trapped samples of the past atmosphere. But one thing, of course, is interesting, because if you are at a high elevation on a mountain, you know the air pressure is low. But if you walk down to the ocean, the air pressure becomes higher. So we can simply take the air bubbles and measure the change in pressure in the air bubbles. So we can see here at the the onset of the Amiens going out of the previous interglacial, we have an air pressure of about 80. But as the period goes, there's a lowering of the surface, and you can see that we end up with an air pressure of 95. The axis reversed. That's worth noting here. So you can see that the elevation is going down in this period. So if we try to interpretate this curve, we can't really use the central part because it's become so warm that there's a lot of melt layers in the ice. And for the melt layers, the air bubbles are broken, so we can't use that. We can try to translate it. We can look at the change of insulation, and we end up with this blue curve here, showing that on the onset at this period here, about 128,000 years ago, the surface elevation was 220 meters higher than the present, while at the end of the warm period here, the surface had lowered, so it was 100 meters lower than the present surface. So there's been a drop of the surface of 330 meters, and the ice thickness here is 2,650 meters. Then there's a drop of the surface, but it's a little more than that, because when the ice gets thinner, you also have an isostatic rebound of the bottom. So in reality, the surface the ice thickness has changed with a little more than 400 meters. So based on that, we can say that the Greenland ice sheet did become smaller in this very warm period, but it was less than 25% of the Greenland ice sheet that was lost in this period of 8,000 years, which was more than 5 degrees warmer than the present. And this is a very good point to have in mind when we think about what's going to happen into our future. Now we have many ice cores from Greenland. And here is just a plot of the ice, delta 18 again. For all the ice cores you can see here in Greenland, from Camp Sentry, which was the first core that was drilled in North Greenland, to Die 3 in South Greenland, and the ones in the middle. It's a depth scale here going down, but it's the delta 018 again. So, but it's cut so it doesn't come from the surface, so it's only showing the glacial part of the ice and then the very basal part of it. So the cyan lines here show what the present temperature delta 18 values are. And what you can see is that in all the ice cores, we find ice near the bottom that's warmer than our present. So it's not only from one ice core here, the one we're looking at before, that we find this big warm period. We actually find this Amiens ice in all our ice cores. And this gives a very, very obvious conclusion that there has been ice over Greenland everywhere we drilled an ice core during the Amiens. This is not rocket science, which is simply find the ice, so of course it's been there. And I'll try to show you a movie made by NASA that kind of works a little with this. So I'll just shut up and let you see the movie, hopefully.
For decades, scientists have been probing the Greenland ice sheet from the ground, air, and space. Now a new study uses those observations to see within the ice sheet, laying bare a tale more than 100,000 years in the making. When we look inside an ice sheet, we can see distinct layers formed by thousands of years of snowfall. As snow accumulates, these layers get progressively compacted into ice, which then flows under its own weight. To get a precise history of a particular spot on an ice sheet, scientists drill into it and recover ice cores, which provide a record of the ice's age and what the past climate was like. Seasonal variations, along with ash from volcanic eruptions, show up in the cores, allowing us to date the ice and correlate samples from different sites. To extend this age information across the ice sheet, the best tool that we have is ice-penetrating radar, mounted on aircraft flying low over the surface. Radar transmits electromagnetic pulses into the ice and records the reflected signals, allowing us to track the depth of the layers detected in the ice. Since 2009, NASA's Operation Icebridge has flown over Greenland more than 100 times with a wide variety of instruments, including radar, and produced vast quantities of data, adding to the work from many other missions. This has allowed researchers to generate a three-dimensional map depicting the age of the ice throughout the Greenland ice sheet. This 3D age map shows that 3 distinct periods of climate are evident within the ice sheet. the Holocene, shown here in green, the last ice age, shown in blue, and the Eemian, shown here in red. The top layers from the Holocene period formed during the last 11.7 thousand years and are fairly flat and uniform, though the thickness varies depending on how much snowfall occurred. Below this, deeper within the ice sheet, we see layers that formed during the last ice age. Layers from this period are darker and more complex, having been further squeezed and sometimes folded as they flowed over the rugged bedrock below. Deeper still are layers of ice left over from the warm period before the last ice age, more than 115,000 years ago. Eemian ice can reveal how the ice sheet responded to a period of warmth similar to the one we are experiencing today. Several ice cores have recovered Eemian ice, but it is difficult to interpret. This new map of the age of the ice sheet shows that there is more Eemian ice than expected in northern Greenland, where it may be easier for scientists to collect and analyze. This new analysis reveals a 3D map of the age of the Greenland ice sheet, from the oldest Eemian ice to the layers deposited during the last ice age to the ice that formed during the Holocene. The response of the ice sheet to past climate change led to its current age structure.
So I think that's beautiful, that you can take and extend the data out from the ice cores to all over Greenland. Now they don't get it quite right, because near the bottom, many places in Greenland, the ice is too disturbed and folded for them to trace the layers. So there's a lot more Eemian ice than they get in their reconstruction. So I think I'll end the story talking about the Eemian, just telling that our results show that Greenland doesn't lose more than 25% of its volume during this warm Eemian period, and this doesn't correspond to more than 2 meters of global mean sea level rise. Now the really interesting thing is that the people that go around the world and study the past sea level, they say that the sea level rise during the Eemian was 5 to 9 meters higher than the present. And this is a picture that shows some of the way the evidence has been made. This is a coral reef from Australia here. At the present, it's 3 to 4 meters over the present sea level, but of course at the time when the reef was alive, it's been underwater, and we can date the corals, and we know that they were alive during the Eemian. So based on evidence like that, it's kind of determined that the sea level was 5 to 9 meters higher. Now that's pretty interesting, isn't it? Because if Greenland can only take 2 meters, where does the rest come from? You see, this is something you ought to be able to answer now. Because what could give sea level rise? There's the 2 big ice sheets, right? So if it's not Greenland, it's Antarctica. And there's quite some speculation if Western Antarctica, which is the ice cap over here, if this is the ice cap that has given the big sea level rise. On the picture, it's the bedrock of the ice that's shown in these quite red colors. But the thing that's really interesting is that the bedrock in Western Antarctica is down to 1.5 kilometers under the present sea level. So you can imagine or kind of visualize it as a big iceberg that is grounded in Western Antarctica. If the iceberg loses mass and becomes less thick, at some point it will pop up and float on the water as an iceberg. And when this happens, it's equal to the whole mass of the Western Antarctica being transferred from a terrestrial ice sheet to the ocean in one go. So this is one of the ideas where the big sea level rise could have come from during the Eemian. But there are other places as well. Also, Eastern Antarctica has some areas that could give the big mass loss. But we know from sediment cores around Antarctica that this kind of disintegration of Western Antarctica has happened many times in the past. We just don't know if it happened during the Eemian, because unfortunately, following the Eemian, we had the glacial time, and the ice has been so big during the glacial time that it scraped away all the sediments in the bottom at the places where we tried to drill sediment cores. So we have no records that show if it happened or not. Now I'm going to turn to something totally different. I'm going to talk about volcanic eruptions, because by measuring the electric conductivity of the ice, we are also able to make determined records of the past volcanic eruptions. And because we are actually able to date our ice down to annual resolution, we have a beautiful record showing big volcanic eruptions. This is a busy curve, but the bottom one here shows the global volcanic aerosol forcing, which is equal to the electric conductivity of the ice. And you can see that there are some places that stands out. For example, minus 44 Anidomio, so 44 years before of the birth of Christ. We have the big Okmok volcanic eruption in Alaska. And here, about 1815, we had the big Tambora volcanic eruption in Indonesia. And there have been a few others here as well. But what we can do is we can take data from tree ring growth up here and compare them with the data here of the volcanic eruption. And if we zoom in on this, we can see things like this. That, for example, the big Okmok eruption 44 BC. So this is the ice core at acidity where the eruption has been. And this is a tree ring record that's shown behind it. You can see how after the big event, you get a sequence of layers that are thinner, which shows that it has been a colder summer at these places. And for the Okmok eruption, we find that there's been 10 years afterwards where the summer temperatures have been colder. So this has had great impact, and it's discussed how it has impact for Rome and Caesar, that is part of the reason that the empire collapsed at this time, because they had a period with famine and a lot of people that died in this period. There's been made all kind of climate models over this, trying to show how much colder it was in this period. And you can see the Mediterranean area here. It's kind of 1 to 2 degrees colder here. And here they try to see how much drier it has been, and it's also been a little drier. So it's difficult to use climate models when you go back in these periods, but it does suggest that there is some evidence that it really had an impact. But this was a study the last 2,000 years. And of course, we've had a lot of bigger eruptions if we go further back in time, because the ice core records from Greenland go 120, 130,000 years back in time, but in Antarctica they go 800,000 years back in time. And you can try to look at what we call the volcanic explosive index, VIE, here, and look at the big eruptions there has been back in time, classified by how much material they have burst up into the atmosphere. And then you can see that Okmok here is classified as number 6, and it's something that has a frequency of 50 to 100 years. In the ice cores, we also have Tambora, Santorini, and also Toba, 74,000 years ago. And these very, very big eruptions, like Toba, only happens with about a frequency of 1 every 50,000 years. And it's clear when you look at the impact of these bigger volcanoes here, it's been a lot more than, for example, the Okmok around the birth of Christ, 44 BC. So it's kind of interesting from the ice cores that you can take the knowledge from the ice cores and combine it with knowledge from the tree rings, and try to combine it with the historic events that has happened back in time, and put these things together, and thereby learn a lot about how evolution has been for us human beings. A very special event that we observed, this one is from last year, is that one place in the ice cores we see these, I think the laser pointer is not so strong anymore. We see these very, very brown layers. Normally we don't see the layers, we just measure the acidity in the ice core, but here we can directly see a layer in the ice core. This is from the North Atlantic ash layer that is from Eyjafjallajökull in Iceland, a big eruption in Iceland, so it's not a global event, it's only over Iceland and the North Atlantic. But we see all our ice cores, we see this ash layer. So at this time, which is about 55,000 years ago, Greenland must have been totally brown of ash just when it happened. And then it gets buried, and we find it in all our ice cores. So I think that's also quite an interesting event. Here's a picture more, where you can see that it's been turned a little around, so it's kind of become conglomerates in the ice, which probably not are natural, but something that has formed with time. Now, a next thing I'd like to tell you about is I have to tell you about the greenhouse gases, because it's so amazing that we have these air bubbles that are trapped into the ice core. And if we crunch the ice and try to look at the content of the past atmosphere, we'd get curves like this, where we see the concentrations of CO2. And we can see that before year 1700, we had a base value of about 280 parts per million. But after that, you see the increase of CO2 concentrations in the atmosphere, And now in the more recent time, you can see how well it fits with the values from the remote observation stations as Cap Grim that's shown on this curve here. So we can see that the increase of greenhouse gases has actually happened for a long time before we started talking about it, which is also always surprises me a little that we first have started talking about it, say, the last 50 years. Now we don't only have to look at the recent climate. Of course, we can also go back in time. In this case, we go to Antarctica, where we have records that can go 800,000 years back in time. So here the x is turned the other way, so time goes this way. So we go towards 0, which is the present time. The middle curve is the temperatures, and you can see this is the Amian we've been talking about. And here's the glacial period, and our present Holocene. And you can see that in general the climate has waxed and waned in glacial and interglacial periods back in time. And if you look at the top curve, which is the CO2 concentrations, you can see that in all the warm periods, the value are about 280 parts per million, as we also saw the pre-industrial value was in the other plot. But you can also see that when it goes down in the glacial time, it goes down to 180 parts per million. So there is a natural variability of the CO2 in the ice cores. And this is because the ocean is the big reservoir for CO2. So when you warm the ocean, you release CO2 to the atmosphere, and when you cool the ocean, you take the CO2 down into the ocean. But the interesting or scary thing, perhaps, is that the present values, the value for 2022 is 414 parts per million, which is quite far above this curve here. So here you can see evidence that the last 800,000 years, we haven't had so high CO2 values in our atmosphere. And just to end this story, I think it's quite interesting to see what actually happened during the COVID-19 pandemic. Well, we know that we closed down a lot of industry, we didn't fly a lot, we didn't drive a lot, and this is the curve of the CO2 concentration in the atmosphere from Mauna Loa. And you can see that there is a gradually increasing value to the 717 parts per million we have at present. You can also see the annual cycle, that it's not the same all the year round, there's a small cycle. But you can't really see 2020 and 2021 stand out. But if you then go and look directly at the release of CO2 each year, in this case it's in a gigaton of CO2, you can see that the release under the COVID pandemic dropped with about 2 gigaton right here out of about 34. So there was a small drop right here, but it's really not a lot. And I think this illustrates how much we actually need to do if we want to release or decrease the CO2 in our atmosphere. It's not so trivial. We really have to do a lot before it happens. So I need to start thinking about ending the stories. I want to show you some pictures from our camp at the end. This is the IPCC predictions of how the temperatures will be in year 2100. This is kind of a scenario where we really reduce CO2 in the atmosphere. This is the keep business as usual scenario, the Trump scenario, as we call it. And you can see how warm it actually will become in 2100. You can also see that the temperatures over Greenland will be quite beyond the temperatures we had during the Amian. So we will get into the situation where the Greenland ice sheet starts to melt away. But again, it will take really, really long time for the ice sheet to melt away. And I think there'll go several hundred years where we can still reverse the process if we make it colder again. I don't think we are close to a tipping point. The last curve I want to show of these is the IPCC prediction of what the sea level rise will be in year 2100 for all the different scenarios. So you can see it's between half a meter and 1 meter here. But when this report came out, paleoclimate people like me said they didn't take the evidence of abrupt changes into account that we've seen in our past. And when they published it, they had added this dashed curve here, which shows what happens if we accept that the ice sheets can be unstable. And then you can see that actually there's a very small likelihood, but a very big impact, and with values up to 1.7 meters, if we trick some of the big things in the climate system, like changing the ocean currents or getting a collapse of West Antarctica, or continuing to increase the CO2 levels a lot. Because the way these curves have been calculated is very much based on the observational records for the last 150 years. So they don't really include the long experience of the past that we get from the ice cores. time is running, and I really want to show you just a few slides from our camp. Right now, we're drilling an ice core in the East Grip, the big northeast Greenland ice stream here. This is a map of the surface velocities in Greenland, and you can see that the places where the surface velocities are very high, like the Jakobshavn ice stream here, and here's the very big northeast Greenland ice stream, Negis. So we are trying to drill an ice core now in the ice stream. It's because we want to know more about ice streams so we can get the processes correct, get them into models, and reduce the uncertainty on the sea level predictions. That's our goal. So we had our camp standing at the Name. You saw one of the first slides, you had the metal frame of the dome. It's standing on 16 legs. Here it is. So we put a ring around the legs with 800 bolts, with some holders for skis, and a bicycle wheel cables in the middle, because the bicycle wheel is a neat way of making a strong structure. Then we took the skis into camp and put them down the ramp. You can see the skis, how big they are here. And we ended up, oops, sorry, now I go a little too fast. We ended up having a dome on ski, as you can see here. And I have a small movie, if it works. No, it doesn't. But okay. We moved the camp 400 kilometers over the ice. It was a really, really fun trip. You can see here's the dome. Here's the generator on a sledge, and here's the fuel tank on a sledge. So it was very much like, you know, having your snail house with you on your trip. Every evening we could go into the dome and have a very, very comfortable evening. And then next day we moved it all again. We're very proud of our achievements. So this is our parade picture when we reach the new site where we're drilling now. You see the big dome here with the track vehicle here and all the sledges pulling equipment. When we reached camp, we had to build our structures again, and we decided to do it in a new way, using big balloons that we inflate in big snow trenches we have made with snow blowers. And when they are inflated, we will cover them with snow, and then we'll deflate the balloons and use this as trenches, using the round structure of the surface as a strong structure with no timber. This is a picture of one of the big balloons here. And here's a picture from the company who made it. They are very, very proud of this balloon. Normally they make balloons for CO2 for beer brewing, but they never made such a big balloon. It has a diameter of 5 meters, which is equal to the metro tunnels in Copenhagen, and a length of 40 meters. So after we had put them down, we take snow and blow down on the balloons down here. And in this way, we close the camp. You can see now they're nearly gone, the balloons. And we end up with trenches like this, with a snow ceiling. This is the first time this has been done in a camp. Before, we've always been putting wooden roofs on, and with time the snow accumulates on the roof and the beams start to break. And it's something all other people have been copying now around the world in ice core projects. Here's the system, the ramp down. We walk down here. Here's the drill trench you see on the picture. Here's a vertical balloon, which is an emergency staircase. Here 2 side walks, and here's the ice core buffer. Here's the science trench. Here's a little room where we store the packed ice core boxes with an elevator in this vertical balloon there to safely bring the balloons to the surface. When we look at the East Grip site here, in the middle of the ice stream, we have ice that's flowing with a velocity of 55 meters per year in our camp. And if we take a radioechogram like the one you saw in the NASA movie, you can see how the ice has been torn apart here at the margins. It's really an ice flood that's cutting itself through the ice stream, flowing out towards the margin. And next year, or this year, in 2 months, we'll reach the bedrock. And one thing I'm really looking forward to do is to lower this camera down and see if we can make a movie like this that we did from the old the borehole Name, where you can see how the side of the borehole is and how the bottom is. The small droppings at the bottom, but for the new drill site, we'll have water running in the bottom, and if things are as we expect, then the ice will be sliding so fast that we should see a new part of the bedrock every day. It should move the diameter of the borehole 130 millimeters once a day. So it's going to be really, really exciting. We have reached a depth of 2,400 meters, and we have 260 meters to drill. We'll do that next. We'll start in 2 months. We'll go to the ice and start drilling, and I'm rather sure we will reach the bedrock this year. Just before I show my last slide, I'd just like to draw your attention to how difficult it was to have a camp which we had to close for 2 years during the COVID. This is the big garage tents that are 5 meters high, that are totally covered by snow. This is the dome where the snow goes up to half the dome, but because of the round structure, there is a wind tunnel that we can enter the dome. So it took us actually 6-7 weeks to get the ice camp back in shape before we could start drilling last year. Down in the snow trenches, the roof had come down to 1 meter over the floor. So with a chainsaw, we had to cut snow blocks and manually take them out of the trenches. 1 hour before lunch and 1 hour before dinner, we all went down and helped, and we made a human chain where we threw the blocks to each other. It was our kind of Arctic CrossFit, and I think we moved 130 tons of ice blocks up before we had the camp ready for drill operations again. So that was a really big achievement. The final words is that eScript is an international project. Sweden is also participating, and we bring a lot of young people to our camp, all our PhDs and all our postdocs, and we find that it's one of the most excellent way to educate our students in an international summer school and educate them to be good climate diplomats, which is what we need. We also do a lot of fun things, like, for example, marathon on the ice along the skiway in the camp. And with that, I'd like to thank you for attention, and you can see a movie here showing a little more of the camp. This is the garage that was covered to the roof that you saw in the movie, in the picture from after being left 2 years by itself. So thank you very much.
Thanks, Dorthe, for your wonderful presentation, bringing us into the past of sea levels across the world and the science you are doing in Greenland. With that, I open the floor for questions. Ariel, please.
Well, again, thanks for a great talk. I have a quick question. So you show this amazing plot with the variability over 800,000 years. How well understood is it? What's driving these oscillations?
I mean, we have run a lot of models over this, and we've also looked very carefully what increases first, CO2 or temperature. And I think the main conclusion right now is that we first see a small temperature rise, and then we see a release of increase of CO2, and then we believe we start a positive circle increasing the values. But of course, the big changes are caused by the astronomy theory, the Milankovitch theory, that the insolation, especially in the summer months on the northern latitudes, changed, and this tricks the amount of ice on Earth and changes in general, gets the globe in ice ages and inter ice ages. So, I mean, the big picture is the Milankovitch theory that tricks the glacial and interglacial periods, but the change of CO2 is kind of in play with the temperature change, so they enhance each other.
Thanks.
Over there.
Thank you for the great talk. I'm just wondering, so you mentioned this like a warming of the temperature, that you have this increase of the CO2 because of melting, right? So at the same time, did you consider this albedo of the ice in your model?
I think when we run the climate models, the albedo and especially the sea ice extension is extremely important.
Mm-hmm.
Yeah.
Thanks.
I don't know if that totally answered your question.
Other questions? You showed that you had at different positions on the surface of the ocean, plus 9 millimeters and minus 9 millimeters. Is that explained by surface motions that sustain this elevation difference in the water, or how can that be so different? It must be connected with surface motions, right?
Yeah, I think it surprises people a lot when they see this curve. I mean, when you think about, we have ocean currents, we have the big a North Atlantic circulation in the ocean, then of course water flows downhill, right? So there's enormous gradient on the surface of the ocean, and the gradient that is causing the currents is very much caused by the salinity difference of the ocean. So as you freshen the water in the north by melting, you change the ocean currents, which then changes the slope of the surface. This is part of the reason of the changes, the big scale changes. Secondly, in the Pacific, around these small islands that are so exposed right now, the ocean is not very deep, so the ocean water warms, and the warming gives a thermal expansion of the ocean water well, which is a second effect that is quite big.
Yes.
So I think these are the two dominating effects.
Thank you. Any other questions? The effect of...
There's a few questions up
question
there.
over there. Great.
So my question was regarding the motion of the ice sheet on the Greenland on Greenland surface. So you have a bore well going from the top to the bedrock, right? But is there a vertical profile to the velocity through which the ice is moving? Because I'm worried that your bore well won't be straight.
Yeah, it's a very good question. We know the surface velocities pretty well because of satellite measurements of features on the surface, so it's kind of SAR-based measurements that can reconstruct the surface velocities on the surface. But when we have drilled a borehole, we go back to the borehole many years and we measure how the inclination and azimuth changes. So we follow how the flow of the borehole with time, and this gives a vertical profile of how the ice is flowing. And based on that, we try to make reconstructions. Over most of Greenland, the ice is frozen to the bottom, so the velocity at the bottom is 0. But in the ice stream, there's a significant sliding. So we think 80% of the surface velocity is sliding, and only 20% is kind of shear deformation as we get down towards the bottom. And this is what we're really excited to see at the eScript camp as well, because as it is now, we have only observed block flow of the ice. We haven't seen the big shear zones yet, but it must come. It's very exciting this summer to see what goes on.
Won't you have to drill again a new borehole if it gets deformed too much?
Maybe, but I think we can. That's a game we can continue, right? Yeah.
At least for some years, I guess.
Yeah.
Thank you. When you... get over there, please.
Hello. Thank you for the talk. I was wondering, it almost seems kind of very lucky that we're just able to see the last period of the climate being very warm in Greenland. But I guess it's not luck, that there's a scientific reason that it's there, or not.
Well, we're actually starting a lot of programs right now. I just got a ESC synergy grant to study the age of the real basal ice in Greenland. And the first pilot measurements we've made showed that ice is probably 1 million years old at the bottom. But the ice very near bottom is so mixed and disturbed that we can't get any stratigraphic records out of it. Well, we do believe that the present ice sheet has probably been standing for 1 million years. That's kind of our understanding of it. But I think that's the next era of ice core research, that we learn to date the ice using radiogenic isotopes. One of the really funny ones is krypton 81. There's a Professor Liu in China that measures with cold atomic trapping that we can reconstruct how long time the gas in the air bubbles have been enclosed when we get really near the bottom. So I think that's a new era, that we can date a little lump of ice, and then we can measure CO2 and other properties of the ice as well. So we go beyond the stratigraphic regime of the ice cores.
Amazing.
Thank you. The effect of deuterium, does it actually trace anything similar to the oxygen 18 isotope? Can one see a similar signature in deuterium?
Well, we measure all the
Yes.
water isotopes. We measure deuterium and delta O17 as well. Deuterium is heavy hydrogen, of course. But to a first order, the deuterium record looks very much like the delta O18 record. But then we make a parameter called the deuterium excess, which is equal to deuterium minus 8 times the delta 18. And then we get another proxy that is more related to the source region of the precipitation that we also use to talk about the changes in atmosphere circulation back in time. Yeah.
Very interesting.
And delta 18 delta 17 we simply don't understand.
Yes. Right. All right. Thanks again for a wonderful talk today, and thanks to the audience for being there.
Thank you very much.